Greetings and welcome to another video. So I said I'd make 4 videos on this topic, and this is the 4th one. Just before we get started, a lot of comments didn't go through, even though the comment moderation was set to minimum. So I mean they got held. So I apologize about that. Let's see if there's anything I can do about it in the future. So in the last video, we were taking one discharge of capacitor, this one, and putting it through an inductor, this coil here. And when you do that, when you discharge a capacitor into an inductor, there's a dance that takes place where the energy that's stored electrostatically in the capacitor goes into current in the inductor, establishing a magnetic field. The capacitor goes to 0, and then the field strength is maximal in the inductor, and now the current begins to reverse, and so it feeds because of the displacement current or inductive spike that occurs whenever there's a changing magnetic field. And since the current is flowing in the opposite direction, it puts a negative voltage now into the cap. If the cap and coil were perfectly undamped, then the capacitor would go to negative 10 volts, then it would discharge, and the current here would be 0, it would discharge, and they would just keep going back and forth in perpetuity. In general, there's usually some dampening where this will go from 10 to, say, -8 or -9, and then back to, +7, +8, and it will ring for a while like a bell, and then it will die out over time. A very similar or identical phenomena would be a swing or a pendulum, where when the pendulum is at the top, it's all potential energy that's from the gravitational field, and the ball or swing just sitting there. It goes down, picks up speed, reaches the bottom. Now there's no more potential energy from the gravitational field, but the kinetic energy is maximal. Then it transfers it over to the other side. And if the swing were perfectly undamped, then the oscillation would continue indefinitely. But in general, you see the pendulum slow down over time. I haven't seen a pendulum that doesn't slow down. And just sort of to reiterate that, this write-up has a, if I can get to it, has a nice graph. So here they're talking about the voltage in a capacitor and the amperage in an inductor. And so, just a few things to get out of the way real quickly. So the capacitor discharges, goes negative, goes back to there. That there is the time from one wave crest to the other. You put 1 over that time, and that's your frequency, your resonant frequency. You don't have to do anything to it. It just goes at its resonant frequency. Now, let's say this is 10 volts. Goes to 0. Your amperage is now maximal. Current reverses. This goes negative. Now the current is 0 in the inductor. This discharges. Now the voltage is 0 in the capacitor. This is maximal. And they're showing a perfectly undamped oscillation. And you note that the voltage and the amperage are 90 degrees out of phase. The other reason I should probably get this video out is I've been like hurtling backwards as I try to make improvements. So I want to try to show you something that I thought was kind of interesting, and then hopefully eventually I can make an improvement instead of going the wrong direction. But anyway, so where were we? There was one pulse that we were looking at in the last video. In this video, we'll just run the thing and we'll calculate milliwatts in and milliwatts out. So let's get the really tough one out of the way first. How do we calculate milliwatts in? So the first thing is, what is definition of a watt? So you can go here, and there's all those definitions, and the one we're interested in is 1 watt is equal to 1 volt amp. So 1 volt at 1 amp is 1 watt. 10 volts at 1 amp is 10 watts. 10 amps at 1 volt is 10 watts. So that's the definition of a watt. So to calculate milliwatts in, we need to know volts and amps, and we don't know either right now. So first of all, how will we calculate amps in? Now, you could just put in an amp meter, tomato, tomato. But you know, as Dr. Evil said, you just don't get it, Scotty. You just don't get it. So what's the fun in that? Let's actually calculate the amps. And I've got like a $10 cheap analog meter, and it looked to be within 5% of the calculated value. If I had to go with one that's more precise and more accurate, I would go with this calculated one. Not just because it's a cheap meter. And then I've fried like 3 or 4 $20 digital cheap, you know, multimeter, the amp part on them. And so enough with that. I mean, I could pick up another like $15 multimeter just to fry another ammeter, but I always seem to forget something, and then, you know, there's a 300 volt spike and too many watts and it fries it. It just blows out the fuse. If I could figure out how to change that. All right, I'm rambling, so this is going to be a bit of stuff, but I'll try to explain it quickly. So, you know, and also without having the amp meter, and that gives scoffers plenty of room to scoff, which is fine with me. So I said we want to calculate the amp part first for getting milliwatts in. What's our, you know, the watt is 1 volt amp. What's an amp? So here is an ampere. They have a very formal definition there in terms of number of electrons, but somewhere here they'll show it to us. Here's the more practical one. 1 amp is the flow of 1 coulomb per second, the flow of charge of 1 coulomb in a second. Okay? If you have 1 coulomb flowing in 1 second, you have an amp. 10 coulombs flowing in a second, you have 10 amps. So now, you know, we're dealing with a capacitor. So the next question becomes, what is the charge in coulombs in a capacitor? So if we go to the excellent electronics tutorial site, we get another equation. Q coulombs equals capacitance times voltage. So if you have a voltage of 10 and a capacitor of 1 farad, then you have 10 coulombs. If that 1 farad capacitor then discharged in 1 second, you would have, for that 1 second, a flow of 10 amps. Now we don't have a 1 farad capacitor here. We have a 10 microfarad. I'm actually going to change this to a 4.7, even smaller microfarad capacitor for this video. I haven't done that yet. I haven't looked at it. I don't think that'll go backwards, because barring other factors coming into play, in general, faster good. So as I was, you know, saying, if you have a capacitor of 1 farad at 1 volt, it discharges in 1 second, then you have 1 ampere. You have 1 amp. And this is 10 UF, which is 1/100,000th of a farad. But what if that 1/100,000th of a farad discharged 100,000 times in a second? Then you would have the equivalent, the exact same thing, as a 1 farad capacitor discharging in a second. Except for in this time you had a 1/100,000th of a farad capacitor discharge 100,000 times in a second. So you'd have the same thing. So we know the capacitance here. So the next question becomes, how many times does this discharge in a second? So now we look at our software. So the first thing we see is we pick a variable called on time right now, and I'll have to figure out what we're going to want to set it at with the setup, but right now it's set at 1,450 microseconds, and that time is based off of the resonant frequency of this and looking for a part in the cycle that's beneficial to us. And so here we have our for loop. We say pin 9 high, and that's 500 microseconds. pin 9 is when charge flows into the cap. We make and break the positive and negative lines, as we talked about in the setup for how to make this circuit. And then we just shut those off. And that's, I just left it as 200, well, for a couple reasons, but just make sure it has enough time to shut down, and probably get away with like 50 there. Then pin 8 goes high. Now pin 8 is when we're discharging the cap into the inductor. Pin 8 goes high, as I said, for on time. And then you just shut it off, pin 8, and you just want to give enough time to make sure that pin 8 is shut off before you start the process over again. So if we add up this 500 that we used to charge the cap, 500 microseconds, 200 microseconds, 700, 300, turns out to be 1,000. So that makes it a little bit easier. There's 1,000 microseconds there, and what do we say, 1450. So there's 2,450 microseconds that occur for this to go from here to here. And then the process starts over again. And what's the first thing that happens? You charge the cap again. So 2,450 microseconds. So 1 over that, this isn't the resonant frequency, but 1 over that is the number of times in a second that the cap gets charged. So 2,450 microseconds, and they're microseconds. So divide by 1 million, 1, 2, 3, 1, 2, 3, equals, takes that many seconds for it to go through the cycle once. Now it has a 1 over x button, so let's see if this works. Okay, so in that case, 408 times in a second, this cap it discharges and gets refilled. Now we're interested in the refilled part, because that's the amp flow that we're using. That's the amp flow going into here. So 408 times. So you can see from there we have the start of it, except for we don't have the voltage. So I hope everyone's staying with this. Q equals C times V. So we know how many times, we know the capacitance, and we know how many times it'll discharge in a second. So, you know, let's say there was a 10 UF cap, 480 times, so 480 times 10, it's the equivalent of a 4,000, or what is the equivalent of? Equivalent of 4,080 microfarad cap discharging in a second. So now we just need to figure out the voltage. So at first thought you might say, well, you know the capacitance of this. If your power supply is at 10 volts, then you know the voltage is 10 volts going into the cap, simple. But I mean, recall this. And I think, mainly before we were showing the cap going down to as far negative when I was doing the single pulses. So let's say you have a 10 UF cap here, and then it goes 0, and then you stop it and you interrupt it there. Now you're at negative 10, and so to get back to 10, you need 20 volts. Now, again, this is a perfectly undamped oscillator. Right? So let's say you stop it here. Now it started at 10 volts, and it's at 10 volts. You have a 10 volt power supply. There's 0 across there. And so now it takes 0 amps because there's 0 volts. And so that's why I'm saying, you don't very often see something like a photon might be an example, but a perfectly undamped oscillation that just continues on in perpetuity. So what we were looking at before was stopping it there. Now, what we're going to set the timing for here is to stop it at this point where it's not going to make it back to there. It will make it to there, and then when you load it, it's going to distort and dampen the oscillation even more, so you only may make it back to like there. And so you have to figure out what the voltage is that the cap ends at. And just to kind of drive that home once more, we'll just do one pulse. So if we And I'll go back to this resonant frequency calculator that we'd set up before. We'd measure the millihenries. There's your capacitance. There's your resonant frequency. That's the resonant frequency, not how many times the capacitance. In this setup, it was 1509 microseconds for it to go most negative. I was at 1450. I was probably just fishing around, or maybe I didn't measure something perfectly accurately. But when we do one pulse through there, you see the cap starts at 10.01, and goes to negative 8.92. So, maybe you could get it to negative 9 if you fish around a little bit, but not too shabby. But that doesn't really help us, does it? Because now, when you come out of this, the cap's at negative 9, so you'd need 19 volts into there to refill the cap. So if we double this time from 1450 to 2900, then this should be where the cap makes it as close back to 10 as it's going to get. And again, I think I can do a bit better than that. I mean, I've seen like 8 or so. But now that's better, because now you only need to put in a little bit more than 2.5 volts to get it back. Now this number is going to change when you put in your secondaries and you load things. The circuit is going to become more damped. So maybe you'll only make it back to 5. But that's 5 other volts that you don't have to deal with. So, all right, let's set that up now, and then you'll have the whole thing for how you calculate milliwatts in. Okay, so now let's just run this 10 times and get rid of that delay where we were seeing it charge up to 10 volts, because otherwise, that wouldn't be good. So 10 times, and what do we see here? Oh, before I even mentioned that. So now I have the secondaries hooked up, and they're going into these other capacitors from a bridge rectifier. And I have them loaded. So this is a 1K ohm resistor, and I have it bridged across the 2 leads there. 1K ohm resistor on the other, bridged across the 2 leads there. Now again, if I wanted to be deceitful, that could be like a 10K ohm, and then all your numbers would be off, and it would be like, oh, look at how good it's doing. But I could measure it and then shut the camera off and change it again. So the important one was when I showed you how to build the circuit. So you go ahead and do this for yourself. So you have to just believe me, that's a 1K ohm there and a 1K ohm there. And what we're seeing is that with that timing, the capacitor makes it, instead of back to 7.5, it makes it back to 6.5 volts. Not too shabby. I'm going to fiddle around just a little bit with the timing and see if I can do any better than that. That was a pretty good time. So now instead of 10 times, let's run it 1,000 times. And so that's when it's running, and then it releases from there and gives us 2 seconds to read what the voltage out is. So again, it's the same value, 6.43. I think it was like 6.5 before. Let's go 500. They should be the same. I don't know why it's a tiny bit different. So in other words, yeah, 6.43. Maybe I did have the timing wrong. Okay, so adding 10 microseconds. Now we're at 6.47. So that's I think what we were seeing before. So what you can say is now you know the voltage, because you only have to charge it each time from 6.47 to 10 volts. Okay, so I hope everyone stayed with me now. The rest of it will be easy, and then we'll have some fun and we'll look at what we get. So let's throw all this in a spreadsheet and we'll have milliwatts in. So the on time was 2,910. Remember, with all the switching, then we add 1,000. So 2,910, 3,910. And that's microseconds. So 3,910 microseconds. That many seconds, 255.75 times per second, the cap gets charged. It's a 10 UF cap, so that many actual farads. Start at 10 volts. I think we said 6.47 was what it ended at before you need to recharge it. So the voltage that you need to recharge is this minus this. Okay, so now we do the Q equals VC, and the first thing we do is we say that you have a 1.5 to negative fifth farad cap that discharges 255 times in a second. So it's the equivalent of a 0.00255 farad cap discharging once per second. And then what the heck did I do here? That is your voltage that you need to recharge it, 3.53 times that capacitance. So now we know coulombs. And because amps are coulombs per second, so that many coulombs went into the cap per second. So it's that many amps. So we take that and we times it by 1,000, and at last we have our milliamp draw. Then, recall if this swung from 10 back all the way to 10, then, there'd be no power going in. So we take our milliamps and we times it by 3.53. That's our watts in, 31.869. And again, the other way to get the milliamps would be just put a meter on, but no fun in that. So now we know our milliwatts in. Now we need milliwatts out, and that's a lot easier. So let's say we get a voltage out of here. Let's say we get 2 volts out of here and 2 volts out of there. So we'll say, so if we had 2 volts out of each of the secondaries across a 1,000 ohm load of resistance, then Ohm's law, V equals IR, I equals V divided by R. So we want to calculate, again, the amps. So the amps is is V2 divided by 1,000, or 0.002. And that's your amps, times that by 1,000, and you get your milliamps. It just so happens, because we used 1,000 K, that your volts there are identical to your milliamps. If this was a 500 ohm or a 10,000 ohm, that wouldn't be the case. So you could say then you have 2 milliamps. How many then milliwatts out do you have? Watts equals volts amps. So 2 times 2, you have 4 milliwatts out of one, 4 milliwatts out of the other, for a total of 8 milliwatts. So in this scenario, you would have 8 milliwatts out and 31.89 milliwatts in. Now let's set it up, and we'll run it at 5, 10, 20, and 30 volts, and we'll see what we get. The only difference I'm going to make is I'm going to use a 4.7 UF instead of a 10 UF, because I haven't looked at that yet, but I have an idea of what I think it might do, what I think it could do. These, you could keep them as 10 UF. They're really, all they are is smoothing caps, right? I mean, the important thing is the 1,000 ohm load, but I'll make them 4.7 UF anyways. So I measured this as this 4.7 UF is actually 4.65 on the LCR meter. So we go to our calculator there, and we know that we want to be right around 2,057 microseconds, but you know, not to go way out of bounds, but I was reading an article on something like all about circuits, about anti-resonance. Never heard of that one. But what I'm saying is that there is a bit of variability, even to the cycle time, depending on the load. So I'm going to fish around for exactly where we want this with this load. Okay, so I've changed out those caps, and aside from a line breaking, everything's running great. And I came up with about 2030 microseconds for a good spot to run this. The only other thing I'm going to do is I'm going to put a battery there, and I'm not hiding anything. I tried to tape it down. You know, eventually I would super glue the parts together, but then it's going to be real tough to change the windings, and I want to fiddle around with those as things go forward. But again, once we get out to 30 volts, it rattles too much, so I want to put a little weight on it. And to be consistent, I'll have that there the whole time. So now let's run it 5, 10, 20, 30 volts. The first thing, we'll just pulse it once and just charge it for like, 20 seconds. And we're just looking for, oh, you got to compile it, you moron. We're just looking for what's our actual voltage in. So, and we don't need to get it exactly right, but we want to be in the ballpark. A little higher, come on. No, I don't want to go nuts with this. No, okay. 5.002, good enough. So 2030 microseconds, so add 1,000 as we talked about, so 3030, and it's drifted up to 5.004, so that's what we'll go with, 5.004. Now let's run it. So when we run it, we see it goes back to 3.47, 3.48. Right around there. We'll call it 3.47. So we put that in. Now we know our milliwatts in. We're using 7 milliwatts. Now what are we getting out? So now we just turn on these and we put this in the spreadsheet. And from one of them we're getting 1.612. From the other one we're getting 0.73. 0.73. And the reason they're so different, is because I snapped one of these in half, and then I had to super glue it back together. So it has an easy time getting to one of the secondaries, and it has a tough time getting to the other secondary, because it has to go through that cut there. Now another thing, I had calculated that wrong, because I had left this as 10 UF, but we've changed this cap to 4.65 UF, haven't we? Yes, we have. So it's 4.65 UF. So that's our milliwatts in, 3.61. Now we have 1.613, 614, we'll leave it there for now, and 0.73. So milliwatts out from one is that, milliwatts out from the other, total milliwatts out is that. 3.13, and in is 3.6. So if we divide those two, equals that divided by that. So it's 86% efficient, and not too shabby. Now, one of the reasons it's not too shabby, one thing we're going to see some, well, for one thing, I'll just tell you, is this is a full wave bridge rectifier. There's a 0.6 volt drop across each diode. It has to go across two. So there's a 1.2 volt drop. So when you're running at 5 volts, that voltage drop of 1.2 volts across the bridge rectifier is quite significant. So let's see what happens at 10 volts. Okay, so got it dialed into 10 volts. Now let's run it. Okay, so at 10, it snaps back to 6.41. 6.4, 6.41. So 5 milliamps, 19.7 milliwatts in. This thing's really inaccurate, but the lowest it would read would be 10 milliwatts. So that's why there's nothing showing up there. Let's see what we got on our secondaries. Hold together, you darn contraption, hold together. .93, 2.23. Okay, so 3.93, 2.23. Okay, when I put them in the right place. So that's milliwatts out from one, that's milliwatts out from the other, total milliwatts out 20.47. Roll. So that's saying that it's 103% efficient. This is the first time I knew it would be better with the 4.7. I just knew it. 4.7. This is the first time I've seen that at 10 volts. Let's go up to 20. Okay, so we got it dialed into 20, 20.01. We'll use 20.01 because it likes to drift up a little. So 20.01. So we see that it snaps back to 12.15. 12.15. So we put that in for that. Come on, Paul. 0.15. And we see our calculated milliamps are now 12. Okay, so we got a little confirmation. I'm not gonna put another meter on there. 94.81 milliwatts in. What do we have out? 8.76 out of 1. And 5.48 out of the other. So that's our milliwatts out. 106, 94 in, 106. That's our efficiency. Let's go up to 30 volts. Okay, so we have it dialed into 30 volts. Let's run it. Okay, so if this will hold together, I see it snapping back to 18.37. 36. And you see it's I'm calling it 18.37. Okay, so 18.37. That's our calculated milliamps of 17.8. Observe that there. And 207 milliwatts in. What are our milliwatts out? Okay, one leg gives us 12.85. The other 9.27. 9.28. All right. And let the spreadsheet do its thing. 251 milliwatts out, 207 in. And that's the efficiency. So that's my party trick. I hope everyone had fun. Stay healthy, take care. Ciao for now. Bye-bye.